Yeah, welcome to the lecture course on Relativity and Cosmology. We are still dealing with differential geometry because we have to have a formalism at hand that allows us to describe gravity in a geometric way. And this geometric way is, of course, the formalism of Riemannian geometry in a four-dimensional space-time. Now, we have so far done tensor algebra. We have also introduced tensor densities. We have last time discussed Riemann normal coordinates, which are adapted to a freely falling observer. But as you know, we want to have field equations, and for those you need differential operators such as differentiation, then later also integration, and this we have to develop. So section 5.6 is called Tensor Analysis. Now in special relativity we have these Lorentz transformations x prime mu is L mu nu x nu, and the Lorentz transformations, they constitute a constant matrix. Now this also holds for any vector field. So if we have any vector field A prime mu of x prime, then it transforms also with this constant matrix. And it was constructed in this way. But what happens with the derivatives? Let us check. The partial derivative of this is dA prime mu of x prime over dx prime alpha is L mu nu. This is a constant, and then you have to differentiate this, but this depends on x. So you have to apply the chain rule. So you first have to differentiate with respect to x, and then you have to differentiate the x's with respect to x prime. Now this is the opposite transform than this one, and we have seen that this here is given by the contragradient to L mu nu, and we called it L alpha beta, the inverse transposed matrix. So this is L mu nu L alpha beta d a nu of x over d x beta. So that is then the transformation of a partial derivative, and you see in special relativity it still transforms as a tensor. You have these two factors of L, and so this is a 1-1 tensor. Now in general relativity and here in differential geometry, the situation is different, because here we have a much wider class of allowed transformations, not only Lorentz transformations but general coordinate transformation. So in GR we have general coordinate transformations, and so the constant L mu nu is replaced by what we call the P mu nu of x. So constant L mu nu replaced by P mu nu of x. So you can choose it differently at every space-time point. Of course, for vector field we have the analog of these. So we have here that A prime mu of x prime is a P mu nu of x times A mu of x. So far, so good. I mean, this is what we had before, but now the question arises, what happens with the partial derivative? And let's check. So we have here dA prime mu of x prime over dx prime alpha of x prime. Then we have to differentiate the whole right side of the equation. So we have to differentiate this, and chain rule tells us this is dx beta over dx prime alpha times d over dx beta of p mu nu a nu. Now you see here this now also acts on the p, because this also depends on x. So this also acts on p mu nu of x. So that is, you see, we have here now an extra term. Of course, it also acts on this. This is as it was here in the earlier case, but we have now a term that has a derivative of the p. So we have here, I mean, first a term that comes from the a and is analogous to here. We have p alpha beta. Now this is here our p alpha beta. P alpha beta, p mu nu, a nu comma beta, the partial derivative. But now we have an extra term coming from acting on this, and this is plus p alpha beta, p mu nu comma beta, a nu. And you see here, this is a non-tensorial term. I mean, because of this, this partial derivative does not transform as a tensor, because this would be the corresponding tensorial law. Now we have this strange term with a derivative. So what does this mean? This means that partial derivatives by themselves are not of much use as fundamental entities in the field equations, because we want to have equations that are covariant, that have the form of tensors. So we have to modify this. Well, this is a non-tensorial term, if I may call it like that. So the goal now is to construct a derivative, and we shall call it the covariant derivative that transforms as a tensor. So we have somehow to compensate this term. So we have to introduce something with a transformation law such that this here, I mean that this is supplemented by something else that does also not transform as a tensor, but which cancels that. So the goal is to construct a covariant derivative that transforms as a tensor. Now, what non-tensorial quantities did we encounter so far? Well, the most prominent one is the connection or the Christoffel symbols. And in the one of the present exercises, you will calculate the transformation law of the gammas from the x to the x prime coordinates, and you will see that they have an extra non-tensorial term. So I will just give this expression. So for this, use the non-tensorial transformation law of the Christoffel symbols. And this is one exercise that you will deal with, and the result is as follows. So if we use the Christoffel symbols of the first kind, you can also give the result for the second kind. It's as follows. So we have a tensorial term, but there is an additional term of the following form that reads plus g alpha beta p alpha mu p beta mu rho. No? And by looking at this, you already see before doing the calculation that we also have here this first derivative of this transformation, this local transformation matrix. And in fact, if you use this here, and I will also leave this as a brief exercise, then you can show that the following combination transforms as a tensor. So we will have the so-called covariant derivative that we define as follows. So one notation is here to have a semicolon instead of a comma. Another notation is to use here this nabla symbol instead of the partial symbol. but the definition is that, okay, you use the partial derivative, which is non-tensorial and has in the transformation this extra term, and add to it the following gamma term, gamma mu alpha lambda a lambda, so that when you use the corresponding version of the transformation with an upper index, because of that, then it's just 2 lines or so to see that this here corresponds the non-tensorial part here compensates the non-tensorial part there. And this is why we can take this as a candidate for a covariant derivative. So if we formulate laws with the help of this derivative, then we have a covariant equation. Now, to get further under insight, let us go to the various cases, scalar field and also the covectors and general tensor fields. So if we have a scalar field phi of x, then because this has no indices, it does not transform with the p, because phi prime of x prime, as you recall, is phi of x. In that case, the partial derivatives are already equal to the covariant derivative. So here phi comma alpha can be taken identical to the covariant derivatives because they are already covariant. Different situation happens for the covectors. So let me call them b beta of x, given by their components. How do we derive the law, the transformation law for the covectors? We know, or the covariant derivative for this. We know the law for this. We know the law for vectors. Now what we do is we form a scalar by multiplying a covector with a vector, and use the behavior of phi and the vector to derive the behavior of the covector. So let us consider the scalar product, which is a scalar given by a beta of x times b beta of x. And so from this it's clear phi semicolon alpha is a beta b beta semicolon alpha, and so of course anything that deserves to be called derivative has to obey the Leibniz rule or the product rule, otherwise it's not a derivative. So we have then from this a beta semicolon alpha b beta plus a beta b beta semicolon alpha, right? So this we know, of course, we know what this is, but we want to know what this last term is, or not. That is the looked for term. Now that's a simple exercise because here this is here the same, from this rule as phi comma alpha. So it's the same as this comma alpha, and if you apply the standard Leibniz rule, you get alpha a beta comma alpha b beta plus a beta b beta comma alpha. And so you see here, here we insert what is written on top, the definition of the covariant derivative. So we get then from this that this last term, a beta b beta semicolon alpha, is a beta comma alpha b beta plus a beta b beta comma alpha. This is just this here, and then minus this term. This is minus b beta, and then I insert here this from above, which is with the corresponding index names a beta comma alpha plus gamma beta alpha nu a nu. Now you see here these two terms are identical but have a relative minus sign, so these two terms cancel. This cancels against this term, and what is left are two terms which are a beta, b beta, comma alpha minus gamma beta alpha nu, b beta a nu, and this is the same as, okay, the first is just copied, and the second I renamed, I used a symmetry here and renamed the indices, so this is minus gamma rho beta alpha b rho a beta, and also renaming indices so that here we have here a beta everywhere. And so this holds for any a beta, so we can just skip the a beta and we have the result here that b beta semicolon alpha is here the partial derivative minus gamma rho beta alpha b rho. So let me write this here separately, and then you see also the analogy here with that. So we then have b beta semicolon alpha is b beta comma alpha, and then we have a minus gamma rho beta alpha b rho. So that's then the looked for rule for the covariant derivative of the covector. So you see here, if you compare the two, of course the first term is always the partial derivative, and then you have a compensating term with the gamma. Of course here you have to have this summation because this is upstairs, so it must be downstairs, and here it's just the opposite, but you have here this minus sign, which comes, as you see where it comes from. So we have now the covariant derivative of scalar, vector, and covector, and naturally we can extend this definition to a general tensor field. A general tensor field that has a certain number of upper and a certain number of lower indices, and so we apply these rules to each index separately. That means it starts with the partial derivative, and then it has many terms with pluses and minuses depending on the indices. So we can symbolically write down the following. So generalization to a general tensor field. So let me call it T, alpha, beta, and so on, and mu, nu, and so on, semicolon, lambda. So covariant derivative with respect to x lambda. So the first term is then the ordinary derivative. And then let us first write it down with respect to alpha. So to write this down, I mean, you just ignore all the other indices except for alpha, and you apply this rule here. So you have here plus gamma, maybe to indicate this with color. So we have here this is with respect to alpha, and then we have here lambda, rho, t, rho, beta, and so on, mu, nu, beta, and so on. And the same happens for every other upstairs index. And now for say the first index here, we have then minus gamma. So I should also indicate here that we have here the summation over rho, which is here upstairs, and the position of the alpha. And here we have gamma rho lambda mu, and we have here t alpha beta and so on, and we have here rho nu and so on minus. Now, so I think it looks a little bit awkward with all these indices, but I think the rule is clear. You do it, you apply these two rules here separately for every index. So here, I should also have this mu here. Okay. A further important application of the covariant derivative is for the metric itself. Now, the metric is a central quantity, g mu nu, because it gives you the space-time distance. And so what is its covariant derivative? And as you can also see as a simple exercise, if you take g mu nu and calculate the covariant derivative just by inserting the definition, so you have the partial derivative in two terms with gamma, then you will see that they compensate each other, and that this gives 0, and the same is for the other version. So that's an important rule which you must never forget. So this is also called metricity. I mean, you can construct other geometries where this is violated, but in Riemannian geometry this is fulfilled. And it expresses the fact that the metric is covariantly constant. It's not constant in the usual way, but covariantly constant. So the metric is covariantly constant. And this makes the calculational life for us a bit more convenient, because in expressions with different index positions and a covariant derivative, we can raise and lower indices at our will, even if there's a covariant derivative. Yeah, because the metric does not see the covariant derivative. For example, you have something like that, a vector covariantly differentiated in this direction, and so you can write this as g alpha nu a nu. So become better, and so you can, put this g outside the parenthesis, and you have here this. No, so you see here, without this intermediate step, you can directly raise this index here in the derivative without problems, because the g itself is covariantly constant. No? You can also have following things. So, for example, a alpha, you can also raise this index here with the metric, and sometimes we denote it by this. So we write a semicolon also upstairs, and this is g beta nu a semicolon nu, yeah, and so on, whatever you have. No? So that's very important, that we can use the covariant derivative as an ordinary index. So next we will then apply this to a directional derivative along a curve, and generalize the usual directional derivative to covariant directional derivative. To erase. So we apply this rule of covariant differentiation now to a directional derivative along a curve. So we have a curve x mu of lambda. So at the moment this is an arbitrary parameter. Later we will restrict ourselves to an affine parameter. So this would be the tangent vector u. And you know that we can define a directional derivative in calculus by the following. So if you have a say a vector field, you can differentiate it along the curve only, which is defined by the partial derivative along the coordinates, and then we have this derivative of the coordinates with respect to the parameter. Also, you call this with another notation, d mu a mu dx nu over the lambda. Now, of course, this still has this partial derivative, which is not does not transform as a tensor. So it's obvious that we define a proper directional derivative by replacing this partial by a covariant derivative. And so I define a capital D a mu of x over d lambda. Sometimes here this is a small d, but it's always the same, which is defined as e mu semicolon nu dx nu d lambda, or we have here then this other notation with the nabla. Now we can insert here our expression that we have found for the covariant derivative. So this is then a mu comma nu plus gamma mu nu rho a rho dx nu over the lambda. And you see here this first part term here together with this gives the ordinary, the old directional derivative. So we can write this as d a nu over the lambda plus gamma mu nu rho a rho dx nu over the lambda. Now this gives rise to an important definition. You will understand why this is defined this way, namely so-called parallel transport. So if this here is 0, then we call for a certain vector field, then this vector field is parallel transported along the curve. So we have a definition. If the v mu of x over the lambda is 0, and we take here this to be an affine parameter. Otherwise you would have an additional term. And this, if you write this out from this, then this would mean d v mu over d lambda plus gamma mu nu rho v rho d x nu over d lambda, which is our 4 vector that gives you the tangent is 0. No? So if this is 0, then we call this vector field v parallel transported along the curve. Then v mu of x is called parallel transported along x mu of lambda. No? So that's a generalization from the usual case of Euclidean geometry. Now, if this directional derivative does not change, so the tangent vector always point in the same direction, we call it parallel transported. So it's natural to generalize the notion of parallel transport here to the present of curved space, and the covariant derivative is called parallel transported along x mu of lambda. So infinitesimally from this here, I mean you see then that dv mu is minus gamma v times dx. So we have here, we can write it infinitesimally as minus mu gamma mu nu rho v rho dx nu. And this gives you another interpretation of the gamma, which so far you have learned appears in the geodesic equation, and this will play a role in a minute. But here you see this gamma somehow connects different points along the curve in the sense of a parallel transport. And it's because of this that this is called mathematically a connection. Yeah, in a more mathematical way, you could say that if you have such a structure on your manifold, you can define naturally this parallel transport. You can connect different points. Otherwise, if you don't have such a structure, they are just independent. Let us go to space-time in particular. So I mean, this is general, and use proper time. I mean, for time-like observers here as the parameter, and let the vector field that we want to transport be the the tangent vector itself. No? So I mean the v is something general, and the u is the tangent vector, and let us choose this here now to be the same and see what happens. So then it's clear here, I mean this equation gives, I mean, du mu over d tau plus gamma mu nu rho u rho u nu is equal to 0, and that's already a known equation and known to you. That's a geodesic equation of motion. No? We have written it out in the form where u is dx over d tau, so you have here the second derivative, and here you have the first derivatives of x with respect to tau. So this here is the geodesic equation. And what does this equation tell in this context? It tells a geodesic parallel transports its own tangent vector. No? So this tangent vector here is parallel transported along a geodesic. No? So this means a geodesic parallel transports its own tangent vector. Yeah, and that's also the natural generalization from Euclidean space, because in Euclidean space the geodesics are just straight lines, and the tangent vectors, of course, they lie here on this straight line, and of course they are parallel transported in the Euclidean sense. Now in the curved space you have no longer these straight lines, but you have the geodesics that are as straight as possible, and they replace the straight line, and in this sense they have the same property. So they parallel transport their own tangent vector. Now we can also write here this again with the directional derivative, which is it's also sometimes called the absolute derivative. U mu over d tau is u mu semicolon u dx nu over d tau. So these are equivalent ways to write the geodesic equation. So you can also use the nabla symbol. You find all these ways of writing in the literature. But this is the geodesic equation, just written with the covariant derivative. So you can also write it in this way. Okay, this is just put this in front, but some people also write it just as nabla u equals 0. So the notation means, well, this is defined by this expression. So that's the covariant derivative of the tangent vector along the curve. And you see this, of course, this way of writing directly shows that this is a covariant equation, in spite of the fact that there are non-tensorial quantities. This is non-tensorial, and also this here. But this equation itself, as it must, otherwise it would not make any sense to use it, is a covariant equation, and it's neatly written in this form. If you have a non-affine parameterization, just as a side remark, then you have here a term alpha with some constant times u mu. So first power of one factor of the for velocity. Now the last thing to be discussed in this section is the covariant derivative of tensor densities. No? Recall from last time, tensor densities are also important because these are the things to be integrated over, and densities in physics play a prominent role. So we have to also know their covariant derivative. So let us have a look at these. So this is the covariant derivative of tensor densities. Recall we had one prominent example, the square root. I write it for the space-time context where g is negative, so square root of minus g. We have seen the tensor density of weight 1. So tensor, well, actually a scalar density of weight 1. And recall also we had this formula that related the g with the gamma, or the derivative here also of the g, which was here twice gamma mu. So twice, I mean here where you sum over these two indices of the gamma. Okay, this we can also multiply by g, and so we have here the g comma mu, which is this, is 2g gamma mu. Okay, g is not a scalar, so its covariant derivative is not expected to be equal to the partial derivative, but of course we have to know the covariant derivative of the determinant of the metric. So what's that? So what is g semicolon mu? Well, we have seen that the metric is covariantly constant. So g mu nu semicolon rho is 0, and naturally we want to preserve this property for the determinant of the metric also. No? So demand that g semicolon u is equal to 0, no? Because we had g mu nu comma rho is 0. So we should make, or we should tailor the definition such that this result appears. Okay, it's simple because here we have here the partial derivative and we have here one term. So if we just put it on the other side, we get something that is 0. So from this we define that the covariant derivative of g is g comma mu minus 2g gamma mu. So this is what we demand for that. So g, I mean, this is of course you get when making the square of this. This is a density of weight 1, so this is a density of weight 2, and you see we have here also the 2 appearing here. So this will motivate us in a minute to take this as the rule for general tensor density. But let me first apply this here and consider a vector field v mu of x and its covariant divergence. So if we have v mu semicolon mu, of course this one can calculate from the definition, and you can write it in the following form. You can also have this as one of the exercises. So you have the usual divergence, but somehow additional terms with g. So where do you get this from? I mean, you get this from by having the rule with the partial derivative plus that gamma term, and then we have the trace of the gamma term that we replace by this, and this shows in 2 or 3 lines that the divergence of a vector field is given by, or can be written in this way. So if we multiply this by square root of minus g, then we have that this is as follows. So, and we use that g semicolon mu is 0, then we can write it as square root of minus g v mu semicolon u, no? Because here this semicolon does not see here the g. But then from this here, from the line above, we can write this also as square root of g v mu comma mu. So you see here, I mean this is a vector field, so multiplied by square root of minus g, it's a vector density of weight 1, and this has the property that its covariant divergence is equal to its ordinary divergence. This has important applications. For example, later when you do integration, in integrations as in Euclidean space, you have to apply Gauss and Stokes theorem. And Gauss theorem, of course, there you have the divergence, and typically you have then something like that. And then you can rewrite this in this way here, right? And you can somehow separate this out, and you just have the covariant divergence. So this is an important rule to be considered in integration. But now I will write the general definition. So we generalize this here to an arbitrary tensor field. So if we have a quantity with upper indices, lower indices, and covariant derivative, and we call this a tensor density, or we take this to be a tensor density of weight W. Then we define this to be as follows: to have the usual terms as if this were a tensor, but having then one additional term like this one. So this is the definition that works. So the usual terms as if T tilde were a tensor, and then we have additional terms minus W. No, so here we had this the 2 minus W times gamma alpha rho T tilde mu. So that's the definition we employ. We had here already this example, square root of minus g times v mu, and this in fact, this what we found there applies to any vector density. So example, let v tilde mu be a vector density of weight W. Then we have v tilde mu is v tilde mu comma nu plus gamma mu nu alpha v tilde alpha, and we have the additional term minus W times gamma alpha nu v tilde mu, no, from the general definition. And if we then take, for example, degree 1, or weight 1, and setting mu equals to nu, so that we have the divergence. No, then we have mu tilde mu semicolon mu is mu tilde mu comma mu plus gamma mu alpha v tilde alpha minus gamma alpha mu tilde mu. And you see here, I mean, just by renaming the indices or replacing mu by alpha and alpha by mu, you see that this compensates, and this is 0. And you see here that the covariant divergence is the same as the ordinary one. No? So what we have seen for the special case square root of minus g times a vector field holds for any vector density of weight 1. And this is consistent with the above rule here. I don't have to write this down again here, because here, I mean, square root of minus g times v mu semicolon u is the same here as this one. And a similar features apply to the epsilon tensor. The epsilon tensor, as one can show, is also covariantly constant. Okay, so far for this first introduction into tensor analysis, with, I mean, the central concept of the covariant derivative and its relation to the connection and to parallel transport. Our next section then will deal with the one of the remaining important objects, namely the Riemann curvature tensor, which will be related to the second derivatives of the metric, and which will give you an intrinsic measure for curvature. So then, bye bye for this time, and see you next time.